In today's video, we're going to go over all of Chapter 15, Lecture 11. So we're going to go over these three learning objectives, all of our learning objectives for Lecture 11. So we're going to look at our equilibrium constant. We're going to be able to relate the equilibrium constant to relative amounts of reactant and product available or present in an equilibrium mixture. And we're going to be able to manipulate the equilibrium constant to reflect changes in the chemical equation. We're going to write the equilibrium constant in terms of concentration or pressure for a heterogeneous mixture reaction. And then we're going to take concentration measurements, calculate out our equilibrium constant, take our equilibrium concentrations and our equilibrium constant, and solve for another equilibrium concentration. And we'll be able to calculate our equilibrium constant using initial concentrations and one equilibrium concentration. So we're going to start actually calculating out our equilibrium constant, or use our equilibrium constant to calculate our concentrations. Okay, so hopefully at this point you guys know that once you have, or you can take your equilibrium constant, Kc, or even Kp, and get information about relative concentrations or amounts of product versus reactant. So if we have a Kc that's around 1, we have a fairly even amount of products and reactants at equilibrium. But if we have a very, very large equilibrium constant, that means that we have one that favors our product. An example of this that you guys have seen would be the reaction of H2 gas plus O2 gas to produce water. This is a fairly, what we consider a reaction that's so favored that the products are so favored that we consider it a one-way reaction, and that's because it has such a large equilibrium constant. So it has 2.4 times 10 to the 47, which is a very, very large equilibrium constant. So we say that the reaction proceeds nearly to completion. And then if we were to take this reaction and flip it, so if we were to take 2H2O and do what we call water splitting, that is going to be 1 over that value. So the Kc for this particular reaction is 4.2 times 10 to the negative 48. So very, very unfavored. So we would say that the reaction proceeds hardly at all. Okay. Let's also, pretty easy. Just keep in mind that your Kc or your Kp is always going to be products over reactants. So think about what that means in terms of your equilibrium constant. Okay, so that's all of learning objective 1. Let's move on to learning objective 2, heterogeneous equilibrium. So if we have a reaction that has different physical states, so we have things that might be in solid state, the liquid state, the gaseous state, or the aqueous state. So as a note, with our heterogeneous equilibrium, there are things that are not going to be included in our equilibrium expression. So if we have solids or pure liquids, so this is something that's either an S or an L. These are not included in a Kc expression. right? Because C means concentration, so they don't have a concentration. If we want, we can put them in as 1. But they don't have a concentration, so you don't put them in as any other thing. So it doesn't matter how much solid or pure liquid we have, they will not affect our equilibrium at all. Now, as a note, only gases show up in Kp. So, hopefully we already know that, but just in case. Want to go ahead and talk about a couple more notes about our equilibrium constant. So, K is basically the ratio of the forward to reverse rate constants. So we talked about this in our first lecture, but just remember that K is equal to little kf divided by little kr if you have an equilibrium. Okay. Our concentration of our products is in the numerator, concentration of reactants is the denominator. And our concentrations are raised to their stoichiometric coefficients. Okay. Our K expression, our equilibrium constant, is going to be temperature dependent. As you hopefully know at this point, if you have any reaction, whether it's a one-way reaction or an equilibrium reaction, there will be the forward reaction will be either endothermic or exothermic, and the reverse will be the opposite. So we're going to favor a specific side based upon what our temperature is. So we'll look at that a little bit more when we look at Le Chatelier's principle in our next lecture, but just keep it in mind that we are temperature dependent. We're going to favor a specific side when we heat it up. Another thing, we are unitless with our K expression, just keep that in mind. And solids and pure liquids, not in Kc expression. Only gases in Kp. Okay, so these are all very, very important things to keep in mind for our equilibrium constant. Some of these we already knew. Well, hopefully we already knew all of these, but I wanted to just kind of summarize with this. Okay, so let's try and write a Kc and Kp expression for the following reaction. So we have limestone, which is a solid, which breaks down into calcium oxide and carbon dioxide. So if we want to write a Kc expression for this, so we can start out by writing everything. But this and this, those are solids. so they did not get included. So our Kc expression in this case would just be CO2. Alright, because both of these are going to go to 1. Our Kp will be the same. This is our only gas, so it's the only thing that's going to show up in our Kp expression. So in this case, our Kc and our Kp are equal to each other. Okay. We could try another one, because why not? If we have PbCl2 solid in equilibrium with Pb2 plus AQ plus 2Cl minus AQ. This will not be included in our Kc. So our Kc will be Pb2 plus Cl minus squared. And then our Kp is 1. Okay. Next thing we're going to look at, and one of the hardest, most important things we're going to look at, is using what we call the ICE table or RICE table. And we use it to calculate equilibrium constants. So when we're using an ICE table, so the very most important thing from this chapter, we're using it in order to calculate equilibrium, our equilibrium constant, using equilibrium and initial concentrations, or we can use our equilibrium constant to determine our equilibrium concentrations. So this is just a method of calculating our equilibrium constant. Here we have some steps that are involved. So our very first step is to write a balanced equation. Okay. Then we are going to, in step 2, under our balanced equation, we're going to make a table that lists our substance's initial concentration, change in concentration going from our initial reaction to equilibrium, and then our equilibrium concentrations. So we have our initial concentration. Oh, sorry, real quick. This balanced equation, this is our R. Okay. Then we have our initial concentration. So what we start out with before we try and get to equilibrium, this is our I. Change required to reach equilibrium. This would be our change, or C. And then our equilibrium concentrations. Which is our E. Okay, RICE, RICE. Okay, so the purpose of this is to see what we have to do from our starting reaction concentrations to get into our equilibrium concentrations. Remember, we start out with a reaction, we start out high in reactants, low in products, and we level out. So this is our initial. From here to here is our change, and right here is our equilibrium. Okay, so that's kind of what we're looking at with these RICE tables. So we are going to use X to define the concentration of one of the substances. and that's going to be in molarity. So we're going to use X to basically show how we change things. So we can have initial concentration and then that change in X concentration to get us to our equilibrium concentration. Okay? So our next step, we're going to substitute equilibrium concentrations into the equilibrium equation, and we're going to solve for X. This is going to make more sense when we do an example, but we may need to use the quadratic equation. But we will go into that. Okay, then we're going to calculate our equilibrium concentrations and then check our results. Okay, so some things to note when using a Rice table. If we have pressure, so if we're using Kp, we must be in atmospheres. If we're using concentrations, so if we're using Kc, we must be in molarity. We need to pay attention to our stoichiometry. The first thing you should do is balance out your equation, and you should only have one variable. So you want to relate all of your other concentrations to one substance's concentration. We're going to call that X. And then you're going to be using your Kc or Kp to solve for that X. Okay, so let's try an example. This is an easy example. They get much more difficult, but that'll be for our next one. So we've got PCl5 decomposing to produce PCl3 and Cl2. The Kc of that is 0.0211. So we want to use that information, and our initial PCl5 concentration, equilibrium PCl5 concentration, to determine what our equilibrium concentrations of PCl3 and Cl2 are. So the first thing we need to do is we need to write our equation in our table, like so, where we have each of our substances above a table with initial change in equilibrium concentrations. So here we start out with just PCl5, so our initial concentration is 0.250 molar, and we don't have any of our product. Going from our initial concentration to our final concentration, final equilibrium concentration, we have to change by some X amount. And when we do that, our equilibrium looks like this, 2.50 minus x, and then both of these will be equal to x. So this will change stoichiometrically. Now, because we already know what our equilibrium concentration here is, it is 0.187, we can set 0.250 minus x to 0.187. And from here, we can get an x value equal to 0.063 molar. Okay. Now, what we want to do, this one, like I said, is a very easy one. Since we have this information, we want to go ahead and confirm that we have the correct values. So our Kc in this expression, or in this case, would be PCl3 times by Cl2 divided by PCl5. Okay. If we put these values in, our x is 0.063. And then we have 0.187. We calculate this out, we get 0.0212, which is very close to that value, so I'd say we did it quickly. Yay! Okay, let's try another one where we actually solve for our equilibrium constant. So we want to solve for our equilibrium constant if we have the following reaction. So we start out with 5.73 atmospheres of H2 and I2, and at equilibrium we have an HI concentration of 9 atmospheres. Okay, so we have H2 plus I2 going to 2HI. Okay, so we start out with none of our product but 5.73 atmospheres of both of our reactants. Going from our initial, we need to subtract x here, add 2x here. Okay? And that's based on stoichiometry. There's a 1 here, but a 2 here. So for every 1x, so we'll go from 1 mole removed here, 1 mole removed here, 2 moles added here. Okay? So the magnitude of your x will be based on your stoichiometry. Okay, so our change is 5.73 minus x here, 5.73 minus x here, and then 2x here. We have the equilibrium concentration, so we know 2x is equal to 9.00 atmospheres. Right? So now we can say, okay, 2x is equal to 9. X is equal to 4.50. So this gives us our x value. Then we can figure out our H2 concentration, which is 5.73 at equilibrium. 5.73 minus x, which is 5.73 minus 4.5, which equals 1.23. Same thing for I2 at equilibrium. We'll have 5.73 minus 4.50, which is 1.23. We can then put all of this into our Kp expression to solve for Kp. So we have our partial pressure of Hi squared, because it has a stoichiometric coefficient of 2, our partial pressure of H2, and our partial pressure of I2. Our Kp in this case would be 9.00 squared divided by 1.23 times by 1.23, and when we multiply all this out, we get a value of 53.5 as our Kp value. Okay, I will do more examples of ice calculations or Rice calculations using initial concentrations, seeing how our change affects our equilibrium concentration, and there's going to be much more difficult ones than what you've seen today, but that is the gist of it. So, that's everything. Bye, y'all.